Hey there. Welcome to another problem session. So today we are embarking on really the most interesting part of electricity and magnetism. It's called Faraday law and its applications. Faraday law is a really complicated stuff, and it's best to handle it directly rather than hand wavy. Most places just hand wavy. And so if you don't handle it correctly, the way you're going to learn about Faraday law is just some formulas apply here and some other formulas apply over there, and so on and so forth. I want you to have what the law is very clear in your mind. Think mathematically. It's going to take you calculus 3 knowledge to actually appreciate Faraday law. So here is a very standard problem. So what we have here is a magnetic field. This is a big region, assume it's going on forever. And there is a metal plate. Of course, this is just a cross section. Everything is cross section, right? So there's a dimension like that, you can say. And the whole thing is moving to the right. This dimension turns out to be not very important as long as it's large enough. And then this dimension I'm going to call W. Some places it's called L. And as a result of when it's moving, so I'm not talking about when it was at rest and started to move. No, we are looking at, so it came all the way here. Maybe V was increasing, and maybe from this to all the way here, the speed is same. Okay, so V constant. That's what I'm talking about. So in that scenario, what's going on is there will be both protons and electrons that's part of this metal. Okay, they will be moving with V, and they will be experience force from the magnetic field, right? So you remember force, a magnetic field force on a charge is whatever charge is, plus or minus, is part of here, and V cross B. So both protons and electrons can have a charge, but some of the electrons in metal are conduction electrons. So conduction electrons will start to move, and if you use right-hand rule, you will see that the force on conduction electrons will be down like that. So if this is moving this way, force will be down like that. So it's going to pick up. It will have a force downward, and over here it already acted on it. So magnetic field goes on forever. Okay, magnetic field goes on forever. So over there, it actually end up being in this situation. So by the time it enters here, it's in this situation. So you're supposed to assume that by the time I enter this region, we're talking about constant V, is like this. So this part is conduction electrons. So, there's excess electrons here. And over here, there's a shortage of electrons here. So these are all like nuclei of the atoms of the metal. So now, if there was an electron here, and so magnetic force will be this way, and electric force will be this way on that electron, and it will be balanced at this point. Okay, so we're supposed to figure out what will be the relationship between potential here and potential here. So that's the difference between that. Okay, so now that we have it, I think you if you didn't understand what I explained to you, you can rewind it and kind of hear me what I said. try to do this problem on your own, and I'll come back and try to cover what Faraday law is and how I'm going to attack it. There are many ways to do this problem, and I will do it one way. I'll do it starting from the Faraday law. Okay, so we can get this, or we can get okay, we can get that. Okay, see you in just a bit. Okay, so let's review. If you haven't really studied Faraday law, then it's going to be hard. I'm going to just state the Faraday law in a mathematical form. So Faraday law is this statement between electric field and magnetic field, and it's always true. Okay, static, dynamic, doesn't matter. So take a loop. So take a loop. So this is a flat. So the loop is in the flat, and I go this way, and I do a line integral on this loop. So there's a loop on flat space. So this is the flat space. So okay. Or I can take a loop, same loop, but the space space that, so this like a cap, and on the back you have, on the back and let's see. So those patches, and the loop is this going. It's like a cap, and the surface. This is the surface, and over here this is the surface. This is the surface. Yes. And the loop is some C, and this is the loop which is oriented C, and this is the surface. This I'm going to get it from this loop. So over here, because of the right hand rule, you can have a normal integral, a normal that way, but over here on each one of these patches, the normal will be on this patch this way, maybe on this patch is this way, and maybe on this patch over here it's coming out like that. So each patch you have a different normal here. So Faraday law says is that if I take a circulation of electric field, I do this integral over this will be equal to minus of all this surface that this thing is binding, actually minus ddt. So it will be minus d over dt of this integral b n hat dA. Now this integral is flux of B through surface S, and this integral is a circulation of E, right, about C, on C. So how it's circulating around C, and this is how the magnetic field, and then I have to do a minus ddt of the flux. Okay, you got to remember this integral, and you got to know how to do these integrals. And okay, and it's true for any space. So this is any loop in a space. So any loop C in space and corresponding S. So I can just create many S. You can, if I do a different S over here, then I'll have to do this integral over this s. But still will be true, it will still give me the same E dot dl, okay? Because the C is the same. So this is a Faraday law, and the question is how I'm going to use this law over here. So I'm going to try to do the right hand first, and so this will also be called negative of EMF, electromotive force. Sometimes E dot dl minus of that is the EMF of electromotive force. Or you can say voltage around the loop. Voltage around the loop. So if I had a circuit with like this, and if I had a DC voltage V on here, you know, if I go around, if I go from here back to here, I'm going to get a 0, right? So this is, but if I were to go from here and didn't cross the V, then I'm going to get, if I go this way, I'm going to get a minus V. For if I go around, delta V will be between here, this is A and B, so VA minus VB equals to V. If I cross it, then I'm at minus V and then going to get a 0. So in a static situation, if I go around a loop, you're always going to get a 0. But over here, I'm doing the exactly same thing going around the loop for electric field, and I'm collecting voltages, and yet there is a leftover because flux is changing. It's ddt, the rate at change. If flux was not changing, like if this thing stopped, then the whole thing will move around, and then E dot dl will be 0. So I need to find a C and find an S in every problem. Okay, so that's the way to attack it. Find the C and find the A for the problem at hand. So what is the C and what is the E for this problem we need to do? Okay. Okay, so here are a couple of diagrams I drew. At t equal to t, so t equal to 0 is over here, and t equals to t, delta t, it's over here. So right side is quite easy to obtain. B is constant, so is the loop is actually, you can see, expanding. So a delta t loop, this is the loop A prime, and then we can call like C and a D here, C and a D here. So the change is corresponding to that area, and B is B vector is B times k hat, and n hat, because the way I drew the loop, n hat is coming out, n hat is k hat. So when I do this dot product, I just get B, and B is constant, comes out, and so dA is this stuff is the change from here to here is V delta t. So this area, so I have a B right hand side is equal to minus limit delta t goes to 0, B V delta t times this thing is W over delta t. So delta t kind of cancels out, and the limit is just a minus V B W. Left hand side is just this. I have no way of simplifying this more than that. So this is actually minus EMF equals to E dot dl equals to minus BW. So the EMF in this loop, so delta t goes to 0, it becomes that loop. So if this integral around this loop is actually EMF equals to BW, which is equal to minus, if I went, so this is equal to minus, if we do integral d to a plus integral a to b plus integral b to c plus integral c back to d of E dot dl. So this is the integral I need to do for integrals. Okay, so often we say this the EMF is what the voltage will be, but you know, that just, we haven't really proven that. The voltage will be when I do the E dot dl, and if I can find the electric field, then I'll say, I'll make some assumptions and then come to that conclusion, right? So let me erase and then come back to it. Okay, so how do I do these integrals? Okay, well, we can say we go back to this model when the forces, and so over here we can say that this is a infinite plate like that. Too big over there. Infinite plate like that, and this other is infinite plate like that, and this plate, because of these forces we talked earlier, this plate is positive and this plate is negative. And so if you know parallel plates, electric field will be pointed down like that, electric field will be pointed down like that, and everywhere else electric field will be 0. So this will be electric field 0, this will be electric field 0, this will be electric field 0. So when I do this integral, let's see, this will be some E and EY and EY j hat. That's all there will be, this guy. And the loop dA will be 0. A to B is the only place I'm going to be, and this will be 0. This will be 0, so I need to do A to B, and A to B of E dot dl. Now dl is pointed in the j hat direction, so that's like a j hat dy, and so if I do the integration, so this is going to become a this will be minus EY. It's going to be constant. This is going to be constant or uniform. So EY, and the distance between them is W. So electric field along this path is just EY W, and so let's see, this EY full, so this actually EY W. So BVW from here equals to minus EY W, and then EY is minus BV, which says the EY is negative, B is positive, this is positive. That means this is less than 0, which means it's pointed in the opposite as Y direction. So this gives you, this law already gives you what you learned from Lenz's law. Okay, Lenz's law is not outside of this thing. This negative sign is already included in Faraday law. And just Lenz's law is some kind of trick you can play and helps you sometimes solving problem and come up with another principle called some kind of inertia of change or flux. So magnetic flux has some inertia, and if you try to change it, it kind of opposes it. So it has a further interpretation, but when you use Lenz's law to get just minus plus in your current, you're basically overdoing it. It's already included in here. Okay, so EY, the electric field is the direction in which the positive current will flow, right? If there was a circuit here, but there's no circuit here, current is not flowing here. It's just a balancing of the forces. So you can see here, I got EY. So what's going to voltage B minus voltage A will be, remember that E equals to minus del V, and if this is constant, then delta V is just E over the distance over which E times D, I mean E times D. So you can just do the distance, and so it will be EY. This is B is the positive part, A is negative part, times W, and this is going to be BVW. So it's a long story short. You can see that I can actually use this along with this modeling. So this plus model the problem like that. Actually it's plus Fm, magnetic force that leads to distribution of charges this way, plus model the problem, kind of leads to the answer that you probably know from some other studies. Now, an alternative way of doing this is not from starting from there, but the standard way is presented in this website. So if you can go there and study more on this subject. And if you like this kind of like starting from some fundamental principles and carrying out answer, if it improves your understanding, then please hit the like button, and you can subscribe to this channel if you like. Subscribing helps distribute this content a little more broadly. I think I'll see you in another video. I will be carrying more of Faraday law. There are many more interesting problems of Faraday law to do, and that's going to be pretty much end of our electricity and magnetism section, and then we're going to start on optics. Okay, take care, bye.